I'll talk today to you about HPO and also to a large extent about Bayesian optimization. So when Marius and me organized this thing here a couple of times before, I mean, usually we had, I would say, quite a lot of advanced presentations here in the fall school. I think this is not completely different this year, but yeah, we sometimes noticed there was, for some people at least, a lack of a basic introductory lecture to HPO and BO. So I kept this fairly simple. I've kept this fairly to the basics. So either you will like that a lot because you haven't seen this before and your goal is to learn this here a bit, or you will be somewhat bored by this. I guess you will figure this out very soonishly on what side you are. In any case, I'm absolutely open to questions. You can also interrupt me at any point in between. Maybe just, I don't know, raise your hand, shout. I hope I will be able to see you. Just stop me, okay? I'm not sure whether I can answer everything, but at least I will try, okay? So I have, compiled a couple of different, I don't know, subtopics here for HPO and Bayesian optimization. So I will pretty much early on, I'll give an overview of the basic principles of Bayesian optimization, especially the most well-known acquisition functions and so on, how they work, how the surrogate models work in HPO, the random forest and the Gaussian process. And after this, we'll take a look at a couple of, I don't know, extensions like multi-criteria optimization, noisy optimization, and so on. I probably have way too many slides. I also recompiled them yesterday, so I can see a number of 80 in the PDF. So usually for 90 minutes, I need about 30 slides. On the other hand, there are also lots of animations in there, so we'll see how it goes. If I get into time trouble, which is very likely going to happen if I spend another 10 minutes on the 0th slide, I will skip some of the bonus topics at the end. So the last section is on nested resampling. I guess I would like to spend a few minutes on that. So I guess that's important. So maybe not to only talk about optimization, especially if you are more a beginner in hyperparameter optimization. Okay, let's start. So what are we actually talking about here? So we are talking about, hyperparameter optimization, tuning. In the old days, this was also called model selection. And nowadays, I guess it's very often called AutoML. Hyperparameters, which I will usually denote here with a lambda. Can I use that thing? Yeah, I can. These are actually inputs to our learning algorithm I. So I for inducing algorithm, which usually performs something like empirical risk minimization on our training data to find our optimal model parameters. Yeah? So model parameters are an output of the training procedure. Hyperparameters are actually an input to the training procedure. So it's well defined. Yeah? So the algorithm is completely fixed in terms of its behavior. And of course, we all know that hyperparameters can influence the generalization performance quite drastically. And tuning hyperparameter optimization is now the process of finding a well-performing configuration. So usually we are given a bunch of extra information. So usually we assume that the user knows which hyperparameter are the most important ones. And usually most algorithms require something like a region of interest, box constraints for the numerical parameters, the number of levels to look at, or not the number, the concrete levels to look at for categoricals and so on. So usually we assume we have some search space given here. And now the most important thing in order to optimize something is how do we measure quality. And quality is usually the estimated generalization error, which is defined by which learning algorithm do we run, which performance metric do we take, over which search space do we optimize, and which resampling procedure do we take to evaluate that. So usually this is cross-validate your algorithm or do a training validation split, train your algorithm with the given hyperparameter configuration on the training set, evaluate on the test, on the validation set with the given metric rho, and use that as a feedback value. And how does that look like from a high-level perspective for our HPO optimizer? So we are optimizing this guy here by iteratively proposing one or maybe multiple new configurations. So the acronym for this will be HPC, hyperparameter configuration. So we lambda plus here. we evaluate that by some form of resampling, and then we update our optimizer. And along the way, because everything here is expensive, and usually this is also being used by our optimizer in some form, our evaluations are stored in some form of an archive, where we have here our configurations together with their associated performance values. Why is this actually a difficult problem in optimization? So I don't know whether you've had some I don't know, mathematical or formal education in optimization, but usually this is even subdivided into different regions in math, right? There's linear optimization, there is convex optimization, there's discrete optimization, and usually you can study them for half a year or a year on their own. So usually, I don't know, in optimization we take a look at properties of the optimization problem, so then figure out a technique that's appropriate, right? So what are the properties of this thing here that we are looking at? I mean, first of all, this problem might be black box, right? So this thing here, well, there's a formula. I guess I could go one level deeper maybe and write it down as a more fine-grained formula. But in a certain sense, this is more or less a computer program, right? So I take my hyperparameter configuration, I plug it into the learning algorithm, I train it, I evaluate that. It feels more like pseudocode than a mathematical formula, right? Usually I don't really have an analytical description of this thing, so I can't really exploit gradients and other things very nicely. Yes, in some instances I can. Some modern HPO variants do that, but usually then I have to tie myself at least to a certain model class. What I want to do here is talk about HPO in a more model-agnostic fashion. Okay, maybe another side comment I forgot in the beginning. So for most of the algorithms later on, I've always tried to select something that is somewhat simple to explain. So it's not necessarily the newest variant I'm going to show for everything, but I'm trying to kind of keep it to the basics so you have at least one easy to understand algorithmic variant in your mind to solve different variants of the hyperparameter optimization problem. Okay, so it's black box. That's usually already not so nice. The next thing is that our evaluation function here usually takes some time. This can run for minutes over hours to days. So usually we operate under a pretty tightly constrained budget. We should also probably not forget that if we evaluate our function, our resampling function, doesn't matter whether you seed that. It doesn't matter whether you always use the same validation set. This is stochastic, okay? And this is a random variable. So if you wouldn't fix a seed, or if you would vary your resampling somewhat, you would get a slightly or more different result, okay? This depends on how many iterations do you run this. Your algorithm, your underlying machine learning algorithm you optimize can be stochastic as well. And it also obviously depends on sample size. Yeah? So quite often, I would say we tend to forget this a little bit, as this makes things like Bayesian optimization and so on more complicated, but I've at least brought some slides on that. The next thing, which is nowadays I would say addressed quite well, is the search space structure here. So many of the classical algorithms assume something like numerical parameters. In hyperparameter optimization, we very often have categorical parameters and also dependence hyperparameters. Maybe let's talk a little bit about extensions of the scenario. So usually this is introduced like I did for optimizing a single machine learning model and its hyperparameter space. Of course, we can also talk about pipelines. I guess everybody who's done some applied machine learning knows that this is quite often quite important to get good performance. So the simplest form of a pipeline would be something like a sequential pipeline, where we do some pre-processing in the beginning on the data before we go into the machine learning model. So this can be something like imputation of missing values. Many of the machine learning algorithms we like can't natively deal with those. It can also be something like factor encoding. I guess these are the two very basic ones. But there can also be more complicated forms of feature extraction going on. So the good news from an HPO perspective is that we can just draw a little box around this sequential pipeline here and still just see it as a machine learning algorithm with some hyperparameters. There are now just more of these, so we can optimize them through the same principle. Guess what is important, but we'll hopefully talk a little bit about this later, is that we should really embed these operations here into a pipeline. So the whole pipeline thing is there so that it can have a training and a predict step, and the thing can be embedded in cross-validation. So don't do these things on the complete data set in a static, I don't know, a priori manner, because you then can easily, I shouldn't say overfit, you should say you can easily have label leakage, yeah, and biased performance evaluation. Yeah? So all of these operations should really be embedded in such pipelines, which with modern software and tools we can usually easily do. More complicated way of writing these things would be something like a DAG, so a graph where we go through different choices here, so different preprocessing operations, different feature extraction operations, and different modeling choices. Can write this in various ways as a graph or as some kind of hierarchical structure. And what usually happens then, if you write this down as a search space, so what happens is that you get an even more complicated. Well, you get more of these dependent hyperparameters, right? So if hyperparameters in there, if I would choose this machine learning model here, for example, I don't know, cut boost, then only in that case cut boost hyperparameters are active. And if I would have chosen, I don't know, support vector machine or something else, the settings for this thing here wouldn't make sense, right? So I have this dependent structure in there, which I can also already have if I'm optimizing a single machine learning model. So I guess the usual examples we use here are, I don't know, kernel-based machines where each kernel has its individual hyperparameters, right? And so we now have this hierarchical structure in there, which that makes the problem even a bit more nasty. Yeah? Except for that, we can also nowadays optimize these complicated beasts. So if categorical and hierarchical hyperparameters are okay, this also doesn't make the problem conceptually, structurally more difficult, which is nice. I guess it becomes even more high dimensional, right? Not in terms of a complete combinatorial explosion. There's not really a complete Cartesian product going on because you have these, I don't know, hierarchical pockets, so to speak, but it definitely becomes larger, right? But the structure, in a certain sense, stays somewhat the same. Okay, so how can we solve this now? We already talked about that this feels like a black box optimization problem. So what can we do in black box optimization? So I think Jan talked a little bit about this yesterday, right? Marius, I couldn't be, unfortunately, here yesterday. So I'll go over this reasonably quickly. You have seen grid search, you have seen random search, either because Jan talked about it or you just have seen it anyway, right? So what are some naive approaches? So we can do this, of course, by, I don't know, manually fiddling around with things. So expert knowledge. Some of us who have, I don't know, worked for 15 years on machine learning have become good at that. But it's even though I can sometimes do this for some models, I have to admit it's it's not the most fun thing. I don't know. I'm totally okay with maybe not trying to automate everything, but what I want to do is I want to bring in, I guess, my prior knowledge. I want to configure systems in data science for what goal they should solve. I definitely don't want to do black box optimization. That's not what I would like to do as an expert. And the other thing is that this is, we should also not forget that these approaches have fairly low reproducibility, right? So how can somebody recreate what you have done in the worst case, maybe in your console, okay, while playing around with the system? Then there are random search and grid search. You have seen this before, so evaluating everything on a regular grid or evaluating everything with a uniform distribution. Super easy to code. I guess some of you have done this. You've coded this yourself. It's fairly nice, but parallelization is so trivial. So this is really embarrassingly parallel. Something maybe not to completely forget about. That's if you have run practical experiments, this is something you usually value. Random search is anytime. From a practical perspective, that's also not so bad. But it's obviously these are not the smartest two algorithms. So if you need some local information to figure out that you have like maybe we are minimizing, some downward peak here where you want to go to, and you need some local information to find this. These two guys will not be very good at this. Okay, test question. Why do we prefer random search? How would you explain this? As I said, I'm going to, as now really mean, I'm now asking questions to the audience. Mario said it's a lecture. Usually in Munich, I wait for 50 minutes if nobody answers. I have become very good at that. Why do you think random search is nowadays a bit preferred?
Because
you were faster.
also to address the challenges associated with cost of compute.
Yeah, maybe. Can we maybe also think a little bit about your projections on the x and on the x1 or the lambda 1, the lambda 2 axis? Yeah.
Yeah, we had an exam yesterday, like one had a curve that was very important. Not.
Yep.
So you wasting a lot of computational powers to also try to figure out which hyperparameter we should select for the not problem. So while maybe one line would be enough to figure out the x axis, the embodied hyperparameter would be enough. We also figure along the line.
Yeah. So if one of these two guys here has completely zero effect on anything, we've basically we have an effective budget here of square root, I guess, of 100 in this instance. I guess it might be 10 times 10 on both sides. And here, if you would project on an axis, you still get the complete budget. Yeah. I mean, the other things, I would say that this is any time is usually also very nice. I like this a lot, that you can continue this. You can run, I don't know, independent workers, that really don't have to communicate at all. That's also nice. Yeah. And in grid search, you always have this, like this, you somehow have to fix this resolution here, and these regular gaps, and if the interesting stuff happens in between, it's not so great, right? Then there's also traditional black box optimization. I don't know, simulate annealing, there meets more old-fashioned evolutionary algorithms have been used also for decades on hyperparameter optimization, various degrees of success. So these are more iterative. Yeah, they really learn the landscape to a certain, I wouldn't say they really learn it, like we are now going to learn the landscape in Bayesian optimization, but they do some form of iterative improvement. Yeah. So either by having a local search procedure where you improve a current point, or you have for evolutionary algorithms, for evolutionary strategies, you have a population-based strategy, right? Where you evolve the population over time to improve its mean performance. And here you would see how this would maybe look like with a larger budget. Yeah, maybe here would be some form of a random search, some form of an evolutionary strategy. Sorry, this is actually wrong. Not with a larger budget, but with a tightly restricted budget. So you see something like a random search here. You see something like a CMAES, so covariance matrix adaptation evolutionary strategy on a super simple 2D mathematical test function. So in this case here, this is the Eckley function. And if I would have this continue for thousands of more iterations, CMAES would, I guess, beat the pants out of these two other guys here, including BO. But it needs some time to get there. So usually these things are not made for these tightly restricted budgets that we are using in, we are only allowed to use in expensive black box optimization. So let's start with the generic VO loop. So how does this work? So how do we motivate that? So we have our black box function f here. This would be our, I don't know, our search region or feasible set S, and we want to optimize this guy. So currently because it's black box, we know nothing about this thing. So I guess we have to start somewhere. So the idea is to at least perform a couple of initial evaluations, right? So you have some form of information and then produce some, I don't know, well-behaved iterative loop. How would that work? Well, I guess if we know nothing about the function and every evaluation is fairly expensive, yeah? And so you kind of want to use all of the information gained from all of the past evaluations to decide what to do in the current one. And if we would know f, we could do something smart with it, right? So how about extracting information might feel like approximating f? Huh? So figuring out at least a rough approximation between the hyperparameters and the output, right? And that feels like potentially nonlinear regression, right? We have a couple of points. We have some data, lambda here, performance values here on the right-hand side. It's like a table. We want to learn the relationship to exploit it in optimization. So this feels like regression, right? We know how to do nonlinear regression, so we fit a nonlinear model to f, and we get some f hat. Okay, but I'm already 3 slides ahead, I guess. So maybe let's spend a few seconds to talk about how we actually create initial points to start the whole process. I would say that this is not the most important component of Bayesian optimization, that there are various different choices. If you want to keep it very simple, just do some uniform random sampling. You can also do things like Latin hypercube sampling or Sobol sampling. What is usually not completely unimportant is the size of the initial design. So this depends a lot on what model you are using and how stable this will work if you use a super small sample size, a super small training set size for the model. Yeah? So usually for GPs, for Gaussian processes, which we'll talk about in some minutes, Gesundheit, there's usually this rule of thumb that you should use something like 4 times the dimensionality of the space to 10 times d. So 10 times d can already be quite large in terms of the budget. So I'm not super sure what you're currently doing in SMAC, but I think you started out with a fairly low initial design, and it's now a little bit larger. That was also, I guess, my intuition that usually the detrimental effect you get from having a degenerated model in the beginning is usually outweighs the benefits you get from becoming a bit more iterative, right? And I think you changed this a bit as well, right? I mean, especially also if you use something like random forest and so on, there's a bootstrap going on. Yeah? So you make your data even smaller, and then you have these tiny amounts of data where you then, I don't know, fit a decision tree on. This will not work very well. So your model will be completely far away from F, and you might not learn any part of the structure at all. So from my personal experience, I usually put something like 10 or 20% of the budget, maybe even in the initial design. Also consider if you're running, I don't know, real-world benchmarks. Very often random search is not so bad on the realistic problems we look at. So spending a bit of the budget into a search like that to get a more stable model, probably not the worst thing ever. Yeah? For the types of designs, so usually something like LHS or Sobol is recommended. It sounds a bit nicer, but from benchmarks that I have seen, the effect is also small. Yeah? And there are even theoretical reasons why random designs might not be so bad, especially for GP-based models. But in any case, to at least explain this, if you have never seen this before, so what is Latin hypercube sampling for? It's pretty simple. So what you would do is you would partition your space into regular bins. So, I don't know, little rectangles, squares here. And then in each column and in each row, you basically just have one point in a square. Okay, this is why this is called a Latin hypersquare. And what this results in is a super uniform marginal distribution. Okay, and this is why this is usually being recommended to get kind of a, I don't know, space filling design property. And yeah, the space filling also comes from a second component of LHS. So there are many Latin hypersquares that we could produce like that. And usually what we like is also something which is called the maximin principle. So this means we would usually like to maximize the minimum difference between 2 points. Yeah? So under all of these Latin hypercube squares, there might be some where some points are fairly close together. So what you want is that this minimal distance between 2 points gets maximized. Yeah? So I guess this is also why we call this space filling. Yeah? Okay, let's go back to maybe the more interesting components of BO surrogate modeling. So I will use this super exciting black box here as a running example. Be a little bit careful also about this. These 1D examples are nice for slides. I guess they are somewhat misleading in terms of what really happens in high-dimensional spaces, okay? Nevertheless, I need them to explain the algorithm. Yeah, we already talked a little bit about this. So we have some initial data. We will now fit a regression model to that. So we now have some f hat. And currently, I'm assuming that I am able to evaluate my data without noise. So I'm actually not really fitting a regression model to that, potentially. I guess I'm fitting an interpolator, okay? So why not? If the points are without noise, I could interpolate them if I don't really want to smooth them. And the idea is now, I now have a function, right? It's cheap to evaluate. My f hat, it's the time I need to pay for an evaluation is what? I don't know. Python or R or C++ needs to perform prediction. This is usually not on the scale of minutes or hours and so on, right? So I can now optimize that. I can run one of the black box optimizers from one of the previous slides, an evolutionary strategy, maybe even something gradient-based, to optimize this with a fairly large budget, because this is a cheap to evaluate function. Okay, we can maybe talk a little bit later about how difficult that is. And we've seen a couple of examples. Then we really evaluate the true point. This will now be the expensive part. Then we adjust our model with new data. We propose a new point again. We evaluate again. We fit our model again. We propose a new point. This is fairly close to what we have evaluated before. Not a lot is changing anymore. We have converged. Success, right? Great, we are done. Unfortunately, this is how our true black box looked like. So we have completely missed this global minimum here because we've kind of locally exploited only this area. And this is where acquisition functions come in and posterior uncertainty. So the idea is, and I would say that this is one of the, I don't know, cornerstones, most important concepts for everything that goes on in black box optimization. And this is this trade-off between exploitation, so kind of locally improve points which are pretty good already, versus explore parts of the search space where you have not looked before, okay? And usually every black box optimizer somehow tries to address that. And here our idea is to use, I can do more or less air quotes now, a Bayesian approach to build a surrogate model. So we get something like a so-called posterior mean prediction. This is just our regular prediction function. If you get a little bit confused by these somewhat fancy terms and the posterior variance, okay? So either posterior variance, I will use an S hat square, or the posterior standard deviation, which I would just with an S hat, okay? So this would express confidence, certainty in our prediction. But the idea is that this also tells us, can you guys actually see these bounds here? You can, I'm getting a little bit colorblind. I can see them very well on my own laptop, but I can't see them here at all, which would be a shame. But you can see these things because, okay, maybe I should change the color scheme. I guess I'll show this a little bit for the guys in the back row. So there are confidence bounds around this thing here, okay? And the confidence bounds get larger the larger we move away from evaluated points, okay? So we would actually like to use a surrogate model that behaves like that. So the less we have seen in the area, the less confident we are in our prediction. Yeah? So this should be something like a spatial property, so to speak, okay? Because this helps us now to construct our acquisition function, which should have some component built in to motivate our BO procedure to also take a peek at regions where we have never taken a peek before, so to speak, okay? And yeah, one of the usual model classes to employ here is a Gaussian process. So this is usually constructed in a Bayesian manner, where we have here our capital Y, and this would be our outcome variable. And we would model that conditionally on all of the data we have seen, our training data, I guess that makes sense, and conditionally at the point where we now want to evaluate. So this is a candidate point now, okay? So of course we don't know exactly, we want to decide that, but we'll just write that down mathematically for any point, okay? And and the idea is to work now with this conditional random variable Y here. If we use something like a Gaussian process, what we do know is that this thing here, evaluated at a single point X, is, normally distributed, okay? We have seen GPs before, okay? A few of you. Okay, what is the defining property of a GP? I mean, I have the formulas on the next slide, but if you would define a GP in one sentence, how can we maybe do that? Yeah. Yeah, I would like to hear a few more. So every marginal distribution. So a process is basically some indexed random variable, right? And our index set is this X here, right? So it's actually a mapping from X to this random variable, right? And the defining component of a characteristic of a Gaussian process would be that every finite marginal distribution is actually normally distributed, okay? So this is, maybe not this. So this would be a conditional distribution, but one-dimensional, yeah? So if everything that is, every finite marginal is Gaussian, this thing here will be also Gaussian, but we could even do this for multiple points. This would still be Gaussian, and I could also do this unconditionally. This would also be Gaussian, okay? So everything is basically, every interesting thing we can do with finite data is basically Gaussian, okay? Okay, nice. And what we will now do is we will not, so what I've actually done before, so what I want to now construct is something in between the model and the let's propose a point component of BO, okay? And that I want to call an acquisition function that is, again, just a fancy name for, I'll now construct a function that lives on our search space, and I'm optimizing that to propose my new point, okay? And this will be fairly similar to my underlying surrogate model that I fitted, but it will not be exactly the same. I have actually used my surrogate model, so just its prediction as an acquisition function in the example before. Yeah? And this is what led to this premature convergence into this local optimum, okay? So the posterior mean would also be an acquisition function, which you can use, which is not necessarily always totally bad, depends a bit, but what we now want to do is we want to bake in this posterior uncertainty into the process to explore more, okay? So that's the whole idea. So here is a fairly simple variant of that. So this is what we usually call the lower confidence bound. And this is just our posterior mean minus tau times the local standard deviation. Okay, so how does that look like? So here you can see our the dotted line here is our predicted posterior mean, and I now can set tau to 1, I can set tau to 5, I can set tau to 10. So posterior uncertainty in a certain sense now works as a bonus at points x. So the higher the posterior uncertainty and the higher my tau, the more I kind of gain from that in terms of the acquisition function, or the more I'm kind of inclined to evaluate there. And you can see how by setting tau to different values, I can enforce more or less exploration. You can also see here, if I use tau equals 1, I'm pretty much evaluating, this is the LCB here in red, and this is exactly this lower confidence bound, yeah? And if I set it to a high value, I can basically force the process to do exploration on the boundary, okay? Here's another potential acquisition function, probability of improvement. There are some formulas now on there. You can maybe try to understand them, because I would say they are not super difficult. So, okay, let's maybe spend a few seconds on that so you don't just see, I don't know, notation-wise mess here. But we've already talked about that this guy here is a univariate Gaussian, okay? So that's a fairly simple thing. So you can see it here, right? So we are at some point x, and now y of x is this univariate Gaussian. Something that I also forgot before is that it might actually be interesting to look at f-min. So f-min is just the best performance value. So I usually just minimize, so everything is like loss often in machine learning. So this is the lowest value I've seen in my archive. Wouldn't it be nice, or wouldn't it be a reasonable question to ask, what is actually the probability, if I evaluate at x, what is the probability that I improve upon this incumbent in my archive, right? Might be a reasonable thing to do. And to compute this probability, and the higher this probability is, the more I maybe want to evaluate that point. So is it now possible to compute that? Yeah, that's really easy. So I just use my CDF here, so the cumulative distribution function of the standard normal. And here I standardize my f hat. So I do f min minus f hat and divide by the standard deviation, okay? So I can use the CDF of the standard normal. And this, if you have done, I don't know, a tiny amount of probability theory or stats, right? You can immediately see that this thing here is computed by that, right? That's basically it. And visually, we look at this thing here, we mark our f-min here, we look to the left-hand side of it, and that tail probability, that's PI, that's probability of improvement, okay? If f-min would have been here, there would be a much larger probability of improvement, okay? So you just kind of integrate out over this tail probability here. From this definition, you can also easily compute that the probability of improvement at already evaluated points is already going to be 0, because our standard deviation of the interpolating Gaussian process will be 0, okay? How does this now look like in terms of a little animation? So, I guess it's fairly obvious from the definition that we just compute the probability of improving, but we don't really take into account how much we improve at that point, or how much we stochastically improve at that point. That's just whether we get better or not. This very often leads to PI evaluating points quite close to the current f-min. So that happens here actually a couple of times. You can also see this very peaked acquisition function here. We evaluate actually really often there. And then at some point, we explore more. I guess here we are also somewhat lucky that now the point of activity is exactly here, this thing. So all of these things are actually, I didn't make this up, so this is really computed. But I guess there was a certain amount of luck now involved of really evaluating at the global optimum. Okay, And the last acquisition function is, I guess, the most used one, most popular one, so expected improvement. So how does that look like? So the idea is now really to compute the expected value of how much we progress on y, in terms of performance, when we evaluate at x as an expected value. So what we do is we write down f min, so that's our low incumbent value, minus y, and then we clip this at 0 and evaluate the expected value of this. Yeah? So this is a constant, this is a random variable. Okay? So does this make sense? Why do we? Does it? I mean, imagine maybe the thing without the maximum. So you look at f min, you compute the difference to y, okay, and this would be exactly your step forward you would make. Yeah, I mean, y is a random variable. Okay, it has a random output, but who cares? So if you just look at a single sample, so we compare y to f min, and then I don't know, the difference is 1. Yeah, so we do one step forward. So if it's minus 1, we have become worse. So why not just, I mean, that's actually the improvement, right? So just f min minus y? So that makes much more sense, right? So why would I not use that as an acquisition function? This is a little bit weird, right? To use the maximum. So why not use the simpler version? I guess at least some of you have seen BO before, so the other guys are not answering. I guess one should always ask questions like that, right? So otherwise, I mean, these formulas, they should not just, I mean, randomly appear. They should really make sense to us. So let's remove the max. What do we know about expectation? What is expectation of a constant minus a random variable? I mean, expectation is a linear operator, right? I can draw this inside. And expectation of a constant is a constant, right? So if I would later optimize this, I mean, I don't have a whiteboard now, but so this expectation of this thing here without the max becomes f min minus expectation of y. So the f min I can completely ignore, right? Because that's just a constant, and that's not dependent on x. And expectation of y is just my posterior mean. So if I would do that, I would have used, again, posterior mean as acquisition function, and we already talked about that this might not be the smartest thing because of this premature convergence, so there would be no difference. What actually happens now, if you take the max here with 0, which is effectively just clipping the whole thing here at f min, so we compute f min minus y, and now we can either be on the left-hand side of that, so there's a positive improvement, stochastic, or stochastically we are on the right side of, on the wrong side of things, yeah, so on the bad side. But here, if this happens, we basically treat this as being 0. So no, I don't know, so not becoming worse, so to speak. Yeah? So this actually means we treat our uncertainty in the whole thing in a fairly optimistic manner, right? So uncertainty can kind of help us to end up here, 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 and these things then enter the expected value computation. But the worst thing that can happen through the distribution is that we can be exactly as good as f min. That's a pretty unrealistic assumption, right? Why should this be true? It certainly won't be. But what this produces in the acquisition function is that uncertainty is only used, it's only baked into the thing in a positive manner. Yeah? So, and then high uncertainty will result in a higher acquisition function value, so we explore. This is why this is there, okay? The other nice thing is, and this I won't do now, you can write down EI in this through this good old formula here, so in closed form. So maybe let's at least look at the components. So there's this F min in there. We can get that from the archive. That's just our posterior mean. That's our posterior standard deviation. These things here, so this would be the PDF of a standard Gaussian, and this would be the CDF. This is actually not difficult to derive. That's basically partial integration. Univariate partial integration, so I guess you have done things like that in school. Maybe not on Gaussian processes, but this is not hard to derive. Again, if this thing here would be 0, we could show that this that EI at such points, so already evaluated design points, would be 0. Here's another little animation where you can see how this works, so you get this usual behavior of doing some local exploitation and maybe even evaluating at the boundaries and then getting more activity at other points. And you usually get these bumps of activity here at points that look interesting and that are very far away from everything you have evaluated before. So EI, maybe this is not too visible from these pictures here, is a fairly highly multimodal function. So you get something like this in a higher dimensional space, okay? It's not super simple to optimize. It's cheap, okay? But it's not trivial to optimize that. Yeah? So the more multimodal it becomes, and the more you care about actually identifying the optimum, I guess you at least need an optimizer that can do something like that. Has also this global optimization property, at least partially in there. Yeah. Okay. Okay, some summarizing discussion. So under some mild conditions, we can actually prove that if we would use Gaussian processes as a surrogate model, if we would use expected improvement, this actually converges to the global optimum given an unlimited budget, which we usually don't have. We usually are on the other side of things. But what it actually shows is that no region in the search space will ever degenerate to 0 probability of evaluating there. Yeah? So there's always some positive probability of looking at things. So this is actually a fairly exploring type of search strategy, so to speak, okay? So we are never, this algorithm is never completely sure that parts of the search space have become completely irrelevant, so to speak. We can't do this for PI or LCB. So for LCB, this tau constant is pretty annoying. This would be I don't know, let me not say hyperparameter, a control parameter of BO. Yeah? So theory suggests choosing expected improvement. Usually LCB works also quite well in practice if you have some, maybe from a good benchmark, some domain knowledge on how to set the tau. I think that is possible nowadays. And there are a lot of other more complicated things like entropy search, variants of that, knowledge gradient, Thompson sampling, and so on, for which I don't have time today to talk about them. This is okay until here. Reasonably okay. I'm probably very bad in time. I am. I am. Okay. Any questions until here? So we have 35 minutes left. I will not be able to, I guess, do everything now. Maybe you can tell me 2 things you want to hear. So we can talk about surrogate models, would be very basic. We can talk about noisy evaluations, multi-crit, or evaluation of AutoML. I guess that's 4, tell me 2. I want to see some show of hands. You can raise your hand twice. Basic models, GPs and random forests, noisy, what was it? Multi-crit, evaluation. So it's noisy in evaluation? Okay, fine. Maybe we have some time to cycle back to things. Okay, noisy. What happens now? So now we are going to assume that this f of x here, our underlying objective function, is not necessarily deterministic. Okay? So there will be our evaluation of f of x will be subject to some noise. And this noise could be the same at every point x, or it could be different. So I guess in that instance we would call that heteroscedastic. Okay, that's I guess usually the more realistic assumption, which I will get rid of here in my slides, at least for some things, at least for the examples, I guess. So there would be this underlying function here, and we would sample from that, and get points which are like noisy variations of these guys here. So I guess maybe first of all we should probably write down what is now the goal of optimization, yeah? Because this is stochastic, so usually we would say we would potentially, at least one variant of this would be to optimize the mean of things, right? This would be this average function here in the background, and we want to optimize that. Yeah? Now it's even worse, right? We don't know the function, but we also can't evaluate it perfectly. Yeah? So, yeah, I don't know. Many of the old treatments of Bayesian optimization usually assume that things are deterministic, right? Although most of the experiments I have seen and that I have used Bayesian optimization for certainly are not. Yeah? Hyperparameter optimization also is not. We talked about this. Yeah? So our model performance would be a random variable based on data, based on resampling, influenced also maybe by our stochastic learning procedure. I don't know, maybe we're running SGD in the background or something like this. But also the other large area that Bayesian optimization is usually applied to is some form of expensive computer simulation. Okay, I can make that deterministic, but usually this is also based on some is also usually run on top of some RNG-based simulation, right? Okay. So until now we have talked about potentially interpolating models. So surrogate modeling. I guess now I need to go back to. I'll squeeze in a few minutes. Although you didn't want that. So how would a GP look like? One level below, from a more mathematical perspective. So we have these two formulas here, which are our prediction functions for the posterior mean and for the posterior variance. I guess you all didn't raise your hand because you are all already experts in this. You know this very well, or maybe you don't want to be. Can somebody maybe explain a little bit these components here? So what is this k thing here, this lowercase k? How would we call that for a Gaussian process? Come on, don't let me. I know some of you know this. Can I get another cup of coffee? I can go upstairs. There's actually a lot of. What does the GP depend on? What is this lowercase k? It's kernel function or covariance function, right? And what does this encode? This encodes, if I look at x and x tilde, okay? And I look at the associated outcomes, so I don't know, y of x and y of x tilde, this kernel function encodes how strongly these 2 points are, how strongly the outcomes at these 2 points are correlated, right? Okay? So this is the idea. And we have to make a choice here. We have to pick a certain covariance function to encode this correlation. If you imagine now a Gaussian process as some, I don't know, as some functional landscape. Yeah, it's stochastic, okay, but just pick, I don't know, pick one sample. If the correlation is fairly strong. Sorry, maybe actually let's go to something like this. So usually these things look like this. So I don't know, it could be a Gaussian kernel, it could be a Matern kernel. So this is some, I don't know, decaying thing in terms of the distances, in terms of the distance between x and x tilde, okay? I have 2 points here, and the correlation of their outcomes depends on the distance, and especially for the first Gaussian guy, it decays very quickly if I move the points very far away from each other, right? But there are also parameters in there in this kernel function, so the length scales. I guess actually I don't like this slide here a lot because this just has a single length scale, but usually we have length scales for every parameter. Okay? This controls how strong the correlation is. So if this correlation would be fairly high, and what do you think how the induced landscape of the GP would look like? So if 2 points which are very close together, their outcome is very strongly correlated. Maybe 2 points which are even somewhat far away, yeah, where the distance is higher, are still strongly correlated. How do you think the functional landscape would look like? Yes, yeah, exactly. And if I make it in the opposite, right? If even for small distances it's nearly uncorrelated, yeah, can have a very highly oscillating thing, right? Okay. And this is also why we say these are spatial techniques, right? They depend on distances in the input space. Okay? Does that make sense? Unfortunately, you have to pick one of these. What you can do is you can optimize all of the hyperparameters in there, or maybe we should even call them the parameters of the GP. Yeah, so this we can do still by a maximum likelihood principle. This is okay. But a kernel function we usually have to pick. So if things are just numeric, very often we use these Matern kernels here. Yeah? So these give rise to GPs which are 1, 2, or 3 times differentiable in terms of smoothness. Yeah? So this is usually something that's, I would say, somewhat realistic in terms of applications. These things here are actually infinitely smooth in terms of differentiability now. Yeah, so in practice, these guys usually work quite well. Okay, back to these things here now. So this now, here, this cap, so this lowercase k of x, this is the kernel function evaluated at all training data points, comma, the new point x that we're interested in, okay? That's that thing. So that actually measures the correlation between everything in my training data and the point that I'm interested in, okay? This capital K here is just the Gram matrix or the kernel matrix. So that's just correlation between everything in the training data, okay? Yeah, and then unfortunately I have to invert it, which sucks. And which I will not do in practice, but at least I'll write it down in terms of the formula. So we have to solve linear systems in this guy. Okay? And if I would do something like this here, this would actually result in me interpolating my data, okay? This would form an interpolator. That's also not hard to show. If we now want to transform this into a regression approach, then the correlation between a point and itself will not be 1 anymore, right? And what this results in is basically the oldest trick in the book of, I don't know, modeling, to smooth things out. And this is to add something to the diagonal of this k thing here, okay? And this is what we do to turn this interpolator into a regression model. And this would be, I guess, the first thing we would do if we would do noisy evaluations. Also turns out we can actually estimate this noise parameter, the so-called nugget effect. We can estimate that also through maximum likelihood from the GP. Yeah. The next thing is the acquisition function. So everything we have done in terms of derivation for the expected improvement also assumes that our evaluation function is deterministic. Okay, the Gaussian process itself is some stochastic thing, but the function f we treat it as deterministic. So this also potentially needs to change. Maybe, just to make this a little bit clearer, so you remember the formula for expected improvement, right? I mean, I guess if you don't, we can also go back. Where was it? Here, right? So we, for example, we take that f min from the archive. But that's now stochastic as well, right? So we now, yeah, if we would just use EI, we would use this in a completely unsmoothed out way, right? This could be completely too optimistic just by random chance, yeah? If you want to make a note here, so this is usually called the plug-in value for many of these acquisition functions, and how to treat them is usually not to use fmin, but you use your current model, your current GP, and have it predict on the archive, to get a smoothed out version of the performance values, and usually these are now plugged into these types of formulas, that compute these relationships between the incumbent and the current value, okay? Does that make sense? Okay. Sorry for skipping so much. Maybe I should have stayed on this slide here. All of the formulas on here. So here you can see how you go to the regression model. Adding something to the diagonal here, to my kernel matrix, before it's inverted. Okay. Yeah. You might have also seen this for ridge regression in a similar fashion. Maybe. Or maybe not. And this is, a fairly old noisy acquisition function now. This is called the augmented expected improvement by Wang. So this actually takes the expected improvement with plug-in. So this is the normal expected improvement formula, but it takes this plug-in value of f min, right, where the model is predicted on the archive, and then if min is taken from this archive. So this is now, how old is this now? 20 years. And then it adds in a penalty term here, which is mainly based here on this nugget effect. So to account for diminishing returns of additional replicates as the predictions become more and more accurate. So this is now multiplied with this expected improvement with plug-in term to get us a more or less reasonably well-defined acquisition function for noisy evaluation. Here is one of my, I would say, favorite techniques to do noisy BO. This is also fairly old. Not too many people talk about this. I guess because it is so simple and so unfancy. But this, from my experience, this works very well. This is called reinterpolation. This works fairly well, especially with GPs. So you take your, you now build actually two models. You build a regression model with your Gaussian process with a nugget effect, okay? To smooth out the noise, so to speak. And now you have that model predict on the archive on every point, everything in the training set, and you now exchange y, so the true labels, with y hat, which just gives you a smooth version of your data, okay? You smooth out the noise. And now you fit your Gaussian process again, and then you just proceed as if it would have been, as if the thing would have been deterministic. You can now do simple expected improvement, okay? This is super simple. You can call that somewhat heuristic, but this works quite well. Super simple to implement. You could complain now that this takes twice as much time in surrogate model fitting, right? And fitting GPs is expensive, right? This is somewhat true, but there's even ways around that. So the usual trick is that if you do the length scale optimization of the GP, that's usually the expensive part, yeah, to optimize the kernel parameters of the GP. Usually we fix that for the second round, because just by going to that, and just by going from Y to Y hat usually doesn't change the length scale so much. So we can do that to cut surrogate model training time down quite drastically. Okay? Or maybe you don't care. It's just a factor of 2. Okay. Little multi-crit for the last 20 minutes? Okay. So what is multi-crit optimization? You know, yesterday when I recompiled the slides, I don't know, it's maybe somewhat embarrassing. This happens to me for 20 years. I was sitting in my hotel room. I had, I don't know, quite a lot of, pools to choose from. And when I compiled these slides here, and you can see we are already not going through everything, I usually always have this impression I have to talk for 90 minutes. This is very basic, very boring. I should bring twice as many slides. It's probably enough for two hours, yeah. I don't know, that's still, it has happened to me as a student, apparently we'll never get rid of that. Okay, so multi-crit Bayesian optimization. So we now change our scenario. So maybe there's now not a single performance metric we would like to optimize, but multiple. 2, 3, 4, let's maybe not make it 100, yeah, but maybe a small handful of performance metrics we would like to optimize. Do you think this is realistic in machine learning? Can you maybe come up, this can be used again for arbitrary black box optimization, expensive black box optimization, but I guess here it's about AutoML and HPO. So can you give me a couple of scenarios where you might not be so sure about a single performance metric and would like to use 2 or 3? What could be, I guess one performance metric is always going to be something like predictive performance, right? So you're usually always interested in that. Okay, first question, is it always clear which performance metric to optimize? Okay, I can already see you shaking your head. So what would happen is that we would talk to, either ourselves as the domain expert, or maybe we're working together with a partner, yeah, domain expert, our clients, and you have to ask them, what is actually this metric I want to optimize? Do you want F1? Do you want Matthews correlation coefficient? Yeah, I've heard your data is imbalanced. It's not so clear, right? And they usually don't understand these formulas very well, but you often don't understand their domain. Yeah? And this is usually where the hours go in, right? To figure this out. Maybe even there we would optimize 1 or 2 or 3 of them, right? But then I would say let's say we would have decided together that there's a performance metric that is somehow realistic. Could there be other secondary metrics we might be interested in? Yeah?
The volume resource and there's always some way like it at lower side.
Yes. So, yeah, usually this comes from a technical perspective, yeah, where, we have to, stream over massive amounts of data in prediction. Maybe we want to deploy the model. On a mobile phone, it should be small. Maybe in some cases even training time is interesting because we have to run the thing again a couple of times. That can happen. Fairness. Yeah. Usually if we make our model more fair in terms of machine learning fairness, yeah, this usually has a negative trade-off with predictive performance. Yeah. Maybe things like interpretability, hard to measure, but we're getting closer to being able to do that. Okay, these are all interesting metrics nowadays to look at next to predictive performance. The problem now is that before, if we were just in R1, we can linearly totally sort things, right? We can always say whether a point is better or worse of equal performance. now we have these tuples here. Yeah? So I don't know, for visualization perspectives, let's make them 2D. Yeah? So I'm talking now about the performance values. So maybe I have a point here, I have a point here, and I have a point there, right? And as always, I want to minimize things, right? So maybe these performance metrics would be non-negative, so the optimal point would be here in 0, 0. Maybe I will never be able to achieve that. But what I can certainly say, if I compare a point like that and a point like that, this point here is at least as good in every coordinate as the other guy, and it's strictly better in one. And in that case, I'm always preferring that guy, right? And this is what we would call Pareto dominance. And it's just, again, a fancy term for this pretty simple fact that if we would select from these two things here, we would always prefer this thing, okay? What about this and this point? We don't know, right? This depends now on our preference in terms of performance metrics. Do we prefer models which are more interpretable, or more fair, or do we prefer models which are more better in terms of predictive performance? And again, you could now sit down with your domain expert and have them write down a weighting function, a trade-off function between these metrics. So in my experience, this never works. You can do that, and if you can do this, you can transform this back again into single criteria optimization, right? Okay, so you just optimize the combined thing. What usually works a little bit better is, okay, we don't know how to combine this optimally or realistically. Give me the set of all non-dominated points. So these are all of the points where I couldn't find one that's better. Okay? Pareto better. And I visualize them, and then you can maybe pick. Okay? So maybe you can see, hey, I can actually have a fairly interpretable model by maybe using less features, a low number of effects. But let's say I have features as a proxy for interpretability, amount of features. It's not a perfect proxy. And then you can say, hey, if you go below 20 features, if you go down to 20 features, this is as good as using the 1,000 features from the complete thing. There's a slight drop in performance, but it's 0.01 something, yeah? But below 20, it drops drastically. Usually now people can pick, yeah? Okay? And the idea of these multi-crit techniques, and these are called posterior multi-crit techniques, is to actually compute this Pareto front, so this to approximate this set of non-dominated points, so then users can choose from that. This okay?
So what is like those two criteria? One is minimization, one is maximization, and this graph, like Pareto front will be look like something.
Or maybe it's then more like here above, huh?
Like if one is minimization, one is maximization, might be that can be.
No, I mean in that case you can just multiply your maximization thing with -1 and turn it into something like this, or you just like your ideal optimal point would be in that corner and not down there. Maximization and minimization are transformable into each other. You just multiply things by -1.
Okay, yeah, okay.
It's just no problem. Please ask. It's just it's just annoying to always distinguish between these cases, especially here, where we would have now to distinguish between this for every coordinate. So usually, at least my default is to minimize things. Yeah.
Yes.
And okay, another good thing to have would now be, so usually we have these iterative procedures, okay? They produce points. We can figure out which of these points are non-dominated, but what we would like to have is some quantitative metric again, to measure how good a set actually is. Maybe even the contribution of a point to that set in a multi-crit sense. And one metric that is very, very popular, there are multiple ones, but one that I will talk about here is called hypervolume. And this is also not super difficult. So what you fix is some so-called reference point. So you need that. So this would be the point where in each coordinate it is the worst value of each metric. I don't know if it would be accuracy. Maybe this is 0. Maybe it's, I don't know, 0.5 because you're using this from your balanced guessing model. Yeah? Okay? If you absolutely have no idea what this could be, if you can't come up with, you can take these things here, the coordinates of these points, and add in something like +1, okay? And what you now do is you simply compute the volume between this approximated frontier and this reference point, okay? Not super difficult to write that down mathematically. I actually cut out that slide, but it's just you measure this volume here. This can become computationally intensive if your Y space is higher dimensional, and very often for us it's not, okay? So we can compute that. This is called hypervolume. Sometimes people also call this the S metric, yeah? And yeah, there's now lots of different multi-grid optimizers. Usually these are, they are traditional multi-objective optimizers. There's also nowadays a whole zoo of Bayesian optimization. There's a whole zoo of evolutionary strategies which work in a multi-grid sense. So you might have heard of NSGA2 maybe, okay? So I guess the most well-known one as an EA, but there's also, again, a whole zoo now of different multi-grid optimizers for Bayesian optimization. Yeah, and try to write down something like a taxonomy here, how these things work. So you can, for example, do something like, you can make a decision, do you now model every outcome separately with a separate surrogate model? Or do you somehow combine them in a scalarized fashion? Although we don't know the perfect scalarization. Yeah? How do you generate candidates? And so on. I guess maybe this is a little bit too abstract. I've now kind of selected 2 paths through this maze and selected 2 simple algorithms. So one is here this PAR-ego. This is also now fairly old. This is pretty simple. So what this does is it does not model each outcome independently with an individual GP or with a multi-outcome GP. What it does in every iteration, it performs something like a weighted combination between all of the objectives. This weighted combination is random, okay? So in every iteration, it changes. Also be a little bit careful here. This is not a weighted sum. This is actually a convex combination between a weighted sum and the maximum of the weighted objectives, okay? Okay? And this rho here is usually a smaller value. So this is actually the stronger part in the combination. This is called the augmented Chebyshev norm. And this is also a pretty well-studied function in the theory of multi-grid optimizers. Okay? I can't go into every detail here, but this thing has some nice properties. And what we now do is we basically turn this into a single objective BO problem in each iteration, okay? You draw this random vector, W, and now you run your favorite instantiation of single grid BO on this thing. So you, for example, do 1 iteration of expected improvement. You propose a point, you evaluate it, okay, it has now multiple outcome values, you put in your archive, you draw again another random vector W, and you iterate, okay? Here is how this would feel like visually. So, again, yeah, so some initial design points, the 2 Pareto front in black. We now obtain our scalarized objective. We fit our surrogate model, GP again. We optimize with expected improvement, and we evaluate and evaluate and evaluate. And if we are lucky, we get points here on this Pareto front, or we need a couple of iterations. If you want to have one simple trick to make performance of this thing a little bit stronger, in the beginning of the optimization, do single crit optimization for the individual performance, coordinate functions, so the yj's. Use the w's as, I don't know, canonical base vectors, so 1, 0, 0, 0. So optimized in a certain sense the extreme points of the Pareto font, especially if you do this in a competition where people then use hypervolume to evaluate you. I've seen people winning competitions just by using this trick, okay? It's probably also not totally stupid in real-world applications. It depends on how much you care about exploring the boundary points. Last thing, this is a little bit, I don't know, you could call the other thing a little bit more heuristic. This is maybe a little bit closer to, I don't know, mathematically being well-founded. This is SMS ego. So the S is here again for the S metric. So in a certain sense, hypervolume-based ego. Ego is an old word for Bayesian optimization, okay? So how would that work? So we now, so the idea is to construct, to turn this again into a single objective optimization problem. We like this transformation, and we want to have some form of an aggregating acquisition function. So what we want to do is we want to calculate the contribution of each candidate point x to the hypervolume of our current front. Okay? So ideally, this point would progress the front closer to the origin, to the ideal point, and we want to quantify this progress. So how are we doing that? So here we have our current archive, okay? And just visualize that in Y space, and I can measure the hypervolume, right? The hypervolume would be this green area here, and that's everything behind our current archive. And now I look at some candidate point x. And I will also now model each of my outcomes with an individual GP surrogate model, okay? So for each outcome, just naively, can also use multi-outcome models for this, but in this variant of the thing, just use an individual model for each coordinate. And I can predict now this point into Y space, right? Maybe with posterior mean, okay? What I do instead is I'm again optimistic. I'm using the lower confidence bound, okay? So uncertainty should work in my favor, or should drive me. If there's a high uncertainty, I want to evaluate at that point. And what I now do is I compute what is called the so-called hypervolume contribution. And this is exactly this volume here, which is behind this point, this virtual point, from prediction, and the current front, okay? And this value I take, and the larger that is, the more I'm interested in evaluating that. That's actually my acquisition function. And then there's some technical crap in there to make sure we get a reasonable acquisition function value if the predicted point is behind the front, okay? I'll not explain this now, okay? So that this is not always 0 and we flatline there. Does that make sense? Yeah? This is also, that's a simple thing, and this works also. This is actually quite close to, maybe you've heard of NSGA2. That doesn't really optimize hypervolume directly, but there's also another algorithm which is called SMS EMUA. So EMUA is evolutionary multi-objective, and that does something similar. And this is where this idea comes from. Okay? I'm exactly at 10:29. I covered the 2 topics you chose. Everything you missed is your own fault. No, it's mine. I hope you were able to ask some questions in between. I even asked some to you. You gave very good answers. Sometimes, you were a little bit reluctant, I have to admit. I hope you enjoyed this. Everybody knows about train validation test splits, nested resampling, nested cross-validation. don't optimize on the cross-validation and put it in your papers, okay? Okay? Okay. I hope you weren't completely bored by this. I hope you enjoyed this a little bit. Thank you. Talk to you over coffee in a few minutes.